This is my 10 megahertz interferometer. Look at the previous video, nerds29, for details about this. I have replaced the device under test, which was previously an attenuator, this one, and now instead it's this amplifier, Anzac AMC-147, and the maximum input for this is plus 13 dBm, but then it's heavily saturated. So it is now preceded by attenuators summing up to 19 decibels. And I'm looking at the noise with the interferometer. This is the STRIP screen. I have set the calibration to minus 1.67 to get a reading for the 10 megahertz signal at 0 on the dBm scale. And then I switch on another signal, as I have done previously in the other video. It is 100 kilohertz below here. And when I click on it, I find it comes at minus 60 decibels, 60 dBm. It means it is 60.01. So this signal is 60 decibels weaker than the carrier at 10 megahertz. Then I look at the Linrod screen, and we have this injected signal here, and I have set calibration some time ago. Hopefully it was stable. Yes, so I read minus 60 here. The bandwidth is 1 kilohertz, and I switch off this pilot probe, and now I can read the noise floor in a bandwidth of 1 kilohertz. And it comes out as minus 141. So I connect the spectrum analyzer to this point to see what is the level of the carrier. And as you can see here, hopefully, the level is very close to 0 dBm. It's 0.22 dBm. This means that the noise figure is about 3 decibels. And I think that is in accordance with the specifications for that amplifier. Now I can look at close range, because that is more interesting for this kind of device. I have unbalanced the amplitudes to get a carrier that is reasonably strong in the pursuits. An amplitude margin now of 19 dB. Well, that is satisfactory with a good margin. And I want to send a little bit more on the network. I have to set the level here. And then I look at what is sent to the network in the mode coherent 2, where the carrier within this narrow filter here is used as a reference phase to detect AM and phase modulation, or rather I and Q signals with respect to this carrier. And that is sent to this instance of Linrod. What I have on the screen is this, and I turn the fine adjustment knob on the face. It looks here on the balance like this. And you see, this is the point where the amplitude is minimum. So that's the point where the carrier should be in phase with the carrier that goes through should be in phase with both of the carriers. But an odd phenomenon is now the noise is equal in I and Q, means there is an equal amount of AM noise and FM noise. And this is a little bit unexpected, so I have inserted a phase modulator here, immediately in front of the amplifier, so I can apply frequency modulation. I switch on this generator, 355 Hertz into the modulator, and you can see the sidebands here. But here it's not much visible. You can see it in the red, means the orthogonal channel. It's in the Q channel and very weak in the I channel. I can use this polarization thing to switch the phase. I just rotate 90 degrees. And here you can see how strong this is, frequency modulation. And you can see all the other carriers are fairly close to being frequency modulation also. If I click on this signal and then tell Linrad to find the polarization, it makes some fine tuning because I haven't set the phase absolutely right. And it adapts to something like 105 degrees. It should be 90 because this should be the Q channel. But you can see while optimizing the well, I have clicked on the wrong signal. This was one of the other. The signal generator is here. And here you can see that the phase is different. So these sidebands that originate in the mains frequency are both amplitude and phase modulation, while the signal generator is pure phase modulation. And you can see here the adaptive thing makes a very good suppression of the AM component. And now we can see that the noise is not exactly the same. So when the phase indicator indicates 72 degrees at this moment, I have pure phase modulation. I then click on the noise, let's say here, and Linrad will find what is the phase relation for the noise. And it's clear that there is a definite relation, and you can see here that the correlation between the signals in I and Q is very high. And what this means, I cannot say. But one interesting thing is, no, I thought I saw something of interest. I cannot say I did that. Well, I'm clicking on the 50 Hertz spur. That is 50 Hertz. I get another phase between I and Q, and there is very good correlation. And you can see now the red curve here doesn't have these spurs. But there is one spur that is present. No, maybe. Things are not fully stable. The signal generator is of course present both in the green and the red track here. So the big conclusion is there is a similar contribution from phase noise and amplitude noise at close range. So I go back to the perceives and try to establish the levels of the sideband noise at close range. I'm now looking at a separation of 5 kHz. I have not changed the setting on the generator, and I have not changed the calibration on the SDR IP. And the level I see from the generator is minus 59.98, which is close enough to 60. And the carrier is here, and it comes at minus 0.07. That is probably because I inserted this modulator, which has a loss of 1/10 of a dB or something. I will not worry about that. I don't need that very high accuracy. I want to see instead what do I have here in lean rod. And here something has changed. This is the day after, and I have maybe changed some settings. So I have to set this to show minus 60 again, or rather minus 59.9 to take this loss of the carrier into account. So this will be fine. The bandwidth is, it's 2 kHz. I will reduce it a little bit. Now the bandwidth is 1 kHz, and that did not change calibration, of course. Very little is lost outside the filter. So I switch off the generator, and here is the noise floor in a bandwidth of 1 kHz. Minus 138.1. Here the frequency separation is 950 Hz. I want to avoid the overtones of the mains frequency, the odd overtones. And the bandwidth is 100 Hz, and the noise I see is minus 141 or minus 142. No. Well, minus 142. I have changed the sampling rate for the perceives. It's only 48 kHz now. So I had to recalibrate the S meter because various filters change when I do this. But now it shows minus 60.1 again. And the separation is 100 Hz. And I switch off the extra generator to get the noise floor in 10 Hz bandwidth. At this narrow bandwidth, collecting data is slow. But now I have some points. Minus 140.9. Here is 20 Hz separation, and the bandwidth is 2 Hz. And it's slow and noisy, but I get minus 143.2. Here is a frequency separation of 2 Hz at a bandwidth of 1 Hz. And I observe this minus 135.7. Now that is dBc per Hertz. This is a separation of 1 Hz at a bandwidth of 0.5 Hz. And there is a pattern here I cannot explain, but the average level here and here, when it looks more as expected, is very similar. Minus 135, 34.9 or minus 135.5. I adopt this second value. It looks in a way more reliable. This is 0.7 Hz frequency separation in a bandwidth of 0.1 Hz, and I read minus 140.2. Now I have these data points, and I will plot them in a graph that I have been using before. The AMC-147 has a wideband noise floor here at minus 171 dBc per Hertz. That's given by the noise figure of the amplifier. Then there is flicker noise, like this, at a level of minus 132 at 1 Hertz. It is a little bit more than the noise I have seen in that noisy attenuator, but the oscillators, the red one, which is the citrine, the best I know of from Wenzel, or my oscillators, they are fairly similar, and we can see at frequencies above 2, means 100 Hertz. There is noise added by the amplifier, but not much flicker noise, because this flat noise figure comes from the device not being able to handle enough power. But below 100 Hertz, the noise from the oscillators dominates very much. And normally, low noise oscillators, they are for having a very good stability for measurement of time. And that happens at even lower frequencies. So this amplifier will not introduce any problem with the Allen variation, which is the same as frequency instability, but it does give modulation at higher frequencies. And I think this is well known among people who work with these things professionally, but for me as an amateur it's an interesting discovery. And this curve is at the carrier level of about 0 dBm. And there is some compression. Maybe at the lower carrier level things would look a little differently. But this thing here, if we reduce the carrier level, that will degrade significantly, even though the noise figure might be a little bit better, because there is some loss of noise figure when the unit goes into compression. But I think this is about the optimum one can get from this amplifier.